Hello students, myself Priyanka Mehta, and today I'll be discussing about the binary multiplication based on Booth algorithm. So basically this Booth algorithm will be using the signed 2's complement representation for the numbers. So before I get into the detail of this Booth algorithm, let me first discuss few basic concepts related to the numbers and their representation. So as you all are aware of that the computer hardware understands the language of zeros and ones. Alright. Now usually whenever we want to store any number, let's suppose I want to store a number 8. So definitely the decimal number which I am going to enter with the help of keyboard will be stored in its binary equivalent in the computer hardware. So basically this decimal number 8 will be represented in the form of binary sequence, that is 1 0 0 0. So this is absolutely fine when we are dealing with positive numbers. But what about the negative numbers, or how these negative numbers are actually represented at the hardware level? That is the main question here. So basically at the hardware level we have three different types of representations wherein we can represent a negative number. The first representation is the signed magnitude representation. Second one is the ones complement representation, and third one is definitely the 2's complement representation. So the first one, that is the signed magnitude representation, wherein if a number is negative and we want to store a negative number at the hardware level, in that case whenever we are storing this number in registers, then its most significant bit, that is the n minus 1 bit, will indicate whether the number is positive or the number is negative. So in this particular case, if the most significant bit is 1, it indicates that the number is negative, and if the most significant bit is 0, then it indicates that the number is positive. So this is all about the signed magnitude representation. There are two other different ways of representing a negative number, that is the ones complement and the 2's complement representation. So the ones complement representation says that whenever we are dealing with a negative number at the hardware level, it will be converted into its ones complement representation and will be stored. So how do we take out the ones complement? So let us suppose that we have a binary number 1 1. We need to take out its ones complement. So nothing we need to do. We simply need to reverse the bit sequence. That means the 1 will be reversed by 0 or 0 will be reversed by 1. So if my binary number is 1 1, so its ones complement will be 0 0. So this is how the ones complement representation is done. The third case is that representing a number in the form of 2's complement. So how do we take out a 2's complement? Not a difficult task. We just need to find out its ones complement first and then add 1 to it. So if my binary number is 1 1, I need to find out its ones complement, which will be 0 0. Adding 1 to this will give me its 2's complement representation, which will give me again 0 0. Alright, so I guess this was the basic concepts related to representing a negative numbers. Now I would like to divert you to my area, that is the Booth algorithm. So wherein we'll be discussing its hardware representation as well as one flow chart, that how this entire process of multiplication takes place at the hardware level, and what are the basic steps which we are going to see. So just give me a second, I'll divert my video to my notes wherein we'll be discussing the basic concepts of Booth algorithm, its hardware implementation, its flow chart, and at last we are going to take one example which will help you to show how these multiplications are actually done as far as your hardware level is concerned. So students, let me first discuss that how this binary multiplication actually takes place. So manually how this binary multiplication can be done, that we'll discuss, and later on we are going to see how this multiplication can be done using Booth algorithm. So I have taken one example wherein I have taken two binary numbers this is the multiplicand and this is a multiplier. So before going for this multiplication, we need to consider following 4 rules. These binary rules says that if we multiply a bit 0 with 0, it will give you 0. If a bit 0 is multiplied by 1, it will give me 0. Again 0 is multiplied by 1, it will give me 0. And finally 1 is multiplied by 1, it will give me 1. So what I need to do is I need to apply this simple binary rules in order to find out the final result. So I'll treat my first operand as multiplicand and my second operand as a multiplier. Now I'm going to do just as a simple multiplication method. I'm going to take one by one all the bits of the multiplier. So my first multiplier bit is 0. So what I'm going to do, I need to multiply this 0 bit with all the remaining bits of the multiplicand. So multiplying 0 with 1 gives me 0. 0 multiplied by 1 gives me 0. 0 multiplied by 0 again gives me 0, and 0 multiplied by 1 gives me again 0. Next step is my second multiplier bit, that is 1 in this case. So multiplying this bit 1 with all the other multiplicand bits, so this will give me 1, 1, 0, 1. So these are my partial products which I have generated at each step wherein I am multiplying each multiplier bit with the multiplicand. So this is my partial product first, this is my partial product second. Fine. So I need to add both the partial products to get the final result. Right. Now the Booth algorithm, it requires an examination of the multiplier bits and shifting of the partial products. So prior to the shifting, the multiplicand may be added to the partial product, subtracted from the partial product, or left unchanged according to the following rules. So basically my Booth algorithm will work like I need to examine 2 multiplier bits simultaneously, and based on those multiplier bits I need to decide whether I need to add the partial product with the multiplicand, I need to subtract my partial product with the multiplicand, or need not any change, simply shift operation is required. So these are my 3 conditions which I need to monitor. So the first one is, the first rule says that the multiplicand can be subtracted from the partial product upon encountering the first least significant one in a strings of ones in the multiplier. So whenever I am inspecting the multiplier bits, if the first inspected bit is 1, then in that case I need the multiplicand can be subtracted from the partial product. So what I need to do, I need to subtract the multiplicand from the partial product. The next rule says that if the first bit of the multiplier is encountered to be 0, in that case I simply need to add the multiplicand with my partial product. And the third rule says that if the partial product does not change when the multiplier bit is identical to the previous multiplier bit. So simultaneously I am going to inspect the 2 multiplier bits. So if the current multiplier bit and the previous multiplier bit are same, then in that case I need not to do anything and simply shift operation is required. So this is the hardware implementation of my Booth algorithm. So I have a BR register in which I am going to store my multiplicand. Next I have this QR register wherein I'll be storing my multiplier, and AC register is used to hold my partial product. Complementer and parallel adder would be required for my process. Now Qn and Qn plus 1, these are the 2 bits of multiplier which I need to inspect at each step. So Qn bit is the least significant bit of the multiplier, and which is obviously the current bit under our observation. Qn plus 1 is basically the flip-flop that is going to hold the previous multiplier bit. So I guess we'll take one example so this situation will get clear to you all. So basically I need to do double bit inspection of the multiplier bits. I would also maintain one sequence counter. Now the sequence counter would be set to the total number of bits in the multiplier. So this is my flow chart. So accordingly, we are going to perform the operation to get the final results. So initially, I need to have my multiplicand in the register BR and my multiplier in my register QR. AC, which is going to hold the partial product, is initially set to 0. Qn plus 1, that is the previous bit. So initially Qn plus 1 bit is again 0. SC, that is the sequence counter, it will be set to the total number of bits in the multiplier. So I need to set these three things initially. Now the next step is to check what is the current Qn bit and what is the Qn plus 1 bit. So there are three possible cases here which we have already discussed as rules. So my first rule says that if Qn is 1 and Qn plus 1 is 0, that means Qn here indicates the current multiplier bit and this one is your previous multiplier bit. So if it is equals to 1, 0, in that case what I need to do? I need to subtract my multiplicand from the partial product. So this operation can be done, this subtraction operation can be done using 2's complement method. This can be done like this way also. So AC can be written as AC is equals to AC plus complement of BR plus 1. So I have to perform the subtraction operation. Now if my Qn bit is 0 and Qn plus 1 bit is 1, in that case I need to add my partial product with the multiplicand. Right? And the third case says that if my current bit and my previous bit both are identical, either it could be 0, 0 or it could be 1, 1. So in this particular case, I do not need to perform any addition or subtraction. What I need to do? I simply need to perform an arithmetic shift right operation, and I need to perform this arithmetic shift right operation on registers AC and QR. Now, when you are performing an arithmetic shift right operation, basically AC and QR, we need to shift them to the right and leaves the sign bit in AC unchanged. So when we are performing this shift right operation on AC and QR, so AC is basically holding the partial product. So its most significant bit indicates the sign bit. So we need not to change it. So this will get more clear once we take one example, and at last we have a sequence counter. We just need to check whether sequence counter has reached to 0 or not. If it is not equals to 0, then this entire process will be repeated again, and once your sequence counter is 0, we reach to the end and our final result is in register AC and QR. So I'll take one example and I guess this will give you a more clear picture. So I've taken one example wherein we need to perform a multiplication operation. So there are two operands. The first operand is -9 and the second operand is -13, and we need to consider a 5-bit register. So let us suppose our computer hardware is supporting a 5-bit register. So we need to have their binary equivalent in the form of 5 bits. Fine. So my multiplicand is -9 and my multiplier is -13. All right. Now my BR register, which is going to hold a multiplicand, what I need to do? I need to find out its binary equivalent. But look here. Both the numbers are negative. Now, since the numbers are negative, I need to have their 2's complement, or I need to find out its equivalent 2's complement. So this is what I have found out directly. So this is my 2's complement equivalent of -9. Now, how do I have reached to this? So I have given an explanation over here. So as we all know, the binary equivalent of 9 is 0, 1, 0, 0, 1. Now since we are considering a 5-bit registers, so my 9 will be stored at the hardware level in the form of a sequence of 5 bits. Now here the most significant bit is 0. That means it indicates it is a positive number. Now I need to find out its 1's complement. So taking out its 1's complement, what we need to do? We need to simply inverse the bits. If it is 1, we need to make it 0, and if it is 0, we need to make it 1. So here we get its equivalent 1's complement. Next is we need to find out its 2's complement. So taking out its 2's complement, what we need to do? We need to simply add plus 1 bit to its 1's complement, and this gives me its 2's complement representation of minus 9. This is both are same. So next we have QR register, that is a multiplier, and again it is equivalent to minus 13. So what I need to do, since the number is negative, I need to find out its 2's complement, which I have already taken out. So this particular is the sine 2's complement representation of minus 13. Now initially my AC register, which is holding the partial product, will be 0. Qn plus 1 will be 0 and sequence counter is set to 5. Why? Because these are the total number of bits in multiplier, which is 5 in this case. Now step 1, what we need to do? We need to inspect the first 2 bits of the multiplier given by Qn and Qn plus 1. So my Qn bit indicates the least significant bit of the multiplier, and Qn plus 1 is initially equals to 0. Now since the 2 inspected bit is 1, 0, according to my flow chart, it says that I need to take out the 2's complement of BR, that is the multiplicand, and AC is my partial product. So what I am actually doing, I am finding out the I'm basically taking out the 2's complement of BR and adding it with AC. This is actually wherein I'm taking or I'm subtracting my multiplicand from the partial product. So this is the contents of my AC register. This is the content of complement BR. So BR initially it was equals to 1 0 1 1. So on complementing I'll get 0 1 0 0 plus 1. This give me the final value of AC. Afterwards I need to perform a shift right operation over AC and QR. So whenever you are performing a shift right operation, you need to consider one thing. Here in this AC register, its most significant bit is the sine bit. So I need not to change it. So this bit will remain as it is 0. What I need to do, I need to transmit this 0 bits towards right. So this will become 0, this will become 1, this will become 0, and this will become 0. So its most significant bit, which is 1, will be captured by its least significant bit, that is 1, will be captured by the most significant bit of the register QR, and hence will shift these bits 1 1 position towards the right, and again the least significant bit of QR will be received by flip-flop Qn plus 1, which is equals to 1. In this case we need to decrement the sequence counter by 4. Next step, now again we need to inspect the bit Qn equals to 1 and Qn plus 1 is again it is equals to 1. Since both the previous and current bits are identical, we need not to either subtract or add the multiplicand and partial product. What we need to do, we simply need to make an arithmetic shift right operation. So basically what I need to do, I need to shift the contents of AC and QR. So again I need not to disturb my sign bit, it will remain as it is. Alright, so 0 will remain as it is. This 0 will be transmitted 1 bit position towards right, 0, 1, 0. So again this 0, that is the least significant bit of AC, will be received by the most significant bit of register QR. So 1 1 position towards right, we are going to shift all the bits, and this particular bit 1 will be received by Qn plus 1 during a right shift operation, and next the sequence counter will be decremented by 3. Next step, again we need to inspect the 2 bits Qn and Qn plus 1. It is 0 1 in this case. So what we need to do, we need to add the multiplicand with the partial product, which gives me AC equals to 1 1 0 0 1. Now afterwards I again need to perform a shift right operation. So what I need to do, I need not to change my sign bit. It will remain as it is 1, but this 1 bit will be transmitted towards right. So this will become 1 1 0 0. Its least significant bit 1 will be captured by the most significant bit of register QR. So 1 1 position will be shifting the contents of the register QR, and again Qn plus 1 will receive 0 and sequence counter will be decremented by 2. Next step, again we need to inspect Qn and Qn plus 1. So Qn is 0 and Qn plus 1 is again 0 since both the bits are identical. So again we need not to perform any addition or subtraction, but we need to do a arithmetic shift right. So my AC is 1110. So I just need to shift the contents of AC towards one position right, and I need not to change my sign bit. And my register QR will be this, Qn plus 1 will be 0 and sequence counter will be decremented by 1, which gives the value as 1. The next step where Qn is 1 and Qn plus 1 is 0. So here Qn is 1 and Qn plus 1 is 0. So in that case, I need to subtract my multiplicand from the partial product. So AC will be 0, 0, triple 1. So afterwards, I again need to perform a shift right operation, which will give me AC is equals to 0, 0, 0, 1, 1. So again, I need not to change my sign bit, which is the most significant bit. This least significant bit will be captured by the most significant bit of register QR, and its QR most significant bit will be captured by Qn plus 1. Sequence counter will now be decremented and it has become 0. So once your sequence counter is 0, according to your flow chart, we need to stop here itself and we need to evaluate, or we need to check the contents of register AC and QR, which is equals to this number. Fine. Now, how you can be so sure that the result calculated by you is actually the correct answer? So what we can do, this is the binary representation. So can we find out its decimal equivalent? Obviously, we all can find out its decimal equivalent, which is equal to 117 or 117. So you can cross verify this answer by simply calculating 9 multiplied by 13. So minus minus cancel out and it gives me plus 117. So this is my final answer, and this is how the Booth algorithm actually works. So I just hope that this method is clear to you all. And I just hope that this video will help you to find out how this multiplication takes place at the hardware level using 2's complement method. So good luck to you all. Bye-bye and stay happy, stay safe.